Hello and welcome back to the Biochemistry for Health Sciences channel. In today's video, we shall discuss lipid transport. Just a reminder, we are still talking about the postprandial state of a human. In the last video, we talked about what happens to the lipids in our diet. So the first thing we talked about was the digestion of the larger lipid chemicals, such as triglycerides, phospholipids, cholesterol esters, into smaller components, such as your free fatty acids, glycerol, monoacyl glycerol, lysophospholipids, sphingosine, and so on. Then in the second step, we discussed how the smaller lipid components were taken up by the enterocytes. So once these chemicals are taken up by the enterocyte from the GI cavity, these chemicals can be used by the enterocyte itself. They could be transported into the bloodstream. They could be stored in the enterocyte as lipid droplets, or they could be made into these large lipoprotein particles that are called chylomicrons. And then these chylomicrons are transported into the lacteal vessels, the lymph vessels of the intestine. So in today's video, we'll focus on how these chylomicrons are made by the enterocytes and what happens to the chylomicrons once it enters the bloodstream. And we'll also talk about the other types of lipoproteins besides chylomicrons. So let's look first at the formation of chylomicrons by the enterocytes. So steps here 1, 2, 3, and 4 are basically the digestion and uptake of lipids that we discussed in the previous video. So in the cytoplasm of the enterocytes, the free fatty acids that are absorbed into the enterocytes will combine with fatty acid binding protein, and they will be sent to the smooth endoplasmic reticulum. Similarly, any monoacyl glycerol that is absorbed into the enterocyte will combine with proteins such as retinol binding protein 2, RBP2, and sent to the smooth endoplasmic reticulum. Within the smooth endoplasmic reticulum, MAG acyl transferase will add a free fatty acid to the monoacyl glycerol to form diacyl glycerol, while DAG acyl transferase will add a fatty acid to diacyl glycerol to form triacyl glycerol. The enzyme acyl coenzyme cholesterol acyl transferase, or ACAT, will add a fatty acid to free cholesterol to give you cholesterol ester. Diacyl glycerol, besides being converted to triacyl glycerol, could also be converted to phospholipids by reaction with choline or ethanolamine. After this, the protein called microsomal triglyceride transfer protein, or MTTP, in the smooth endoplasmic reticulum will take all the lipids such as your triacyl glycerol, your cholesterol ester, your phospholipids, and it will transfer these lipids onto the proteins such as ApoB48 and ApoA4 to form what we call pre-chylomicron particles. These pre-chylomicrons are then transported to the Golgi. in the Golgi, triacylglycerol, more cholesterol esters, as well as other apoproteins like ApoA1 could all be added to these pre-chylomicrons to give us chylomicrons. The chylomicrons are then exported out of the cell, out of the enterocyte through the basolateral sites by exocytosis. Chylomicrons are very large particles and they cannot enter the capillaries, so instead they will be transported to the lacteal vessels, the lymphatic vessels of the small intestine. So the chylomicrons will enter the lacteal vessels, and from there they will go to the lymphatic ducts, that is the right lymphatic duct as well as the thoracic duct, which then drain into the subclavian veins, and eventually the chylomicrons will enter the general circulation. So now let's see what happens to the chylomicrons that are now found in the bloodstream, and then after that we'll talk about the other types of lipoproteins besides chylomicrons. So after a meal, chylomicrons are synthesized and eventually they will appear in the bloodstream. Now these chylomicrons are relatively large particles. Microns mean some of these particles can be as large as around 1 micron, that's about 1,000 nanometers. And the presence of chylomicrons will make your blood lipemic. These large particles will give your blood a sort of a milky appearance. And unfortunately, chylomicrons do interfere with many lab tests. And that's one reason why a lot of lab testing is done first thing in the morning before the patient has his or her breakfast, so that we don't have this problem with chylomicrons in the bloodstream. Once the chylomicrons are in the bloodstream, the chylomicrons undergo maturation where they accumulate the apoprotein ApoE as well as ApoC2, either directly from the bloodstream or from other lipoproteins such as HDL. Now let's see what happens when chylomicrons enter tissues such as your adipocytes or your muscle cells. Now tissue cells, especially muscle cells as well as adipocyte, secrete an enzyme. They synthesize and secrete an enzyme called lipoprotein lipase. Now this enzyme has an isoelectric point of around 8. This means that at pH around 7.4 in your cells or in the bloodstream, this enzyme lipoprotein lipase has a lot of positive charges, and therefore it will bind heparan sulfate proteoglycans. These proteoglycans tend to have a negative charge. This lipoprotein lipase HSPG, the proteoglycan, these two form a complex which then dissociate from the plasma membrane and are transported to the endothelial cells that line the blood vessels in the tissue, and this complex will now bind the endothelial cell plasma membrane. There is another protein called glycophosphatidylainositol, HDL binding protein 1, or GP1-HBP1. That's this protein here, and this protein will help to attach the lipoprotein to the surface of the endothelial cells. So now we have this lipoprotein connected to the surface through the proteoglycan as well as through the GP1-HBP1 protein. Now, as the chylomicron travels through this blood vessel, the lipoprotein lipase enzyme, this enzyme here, will bind to the protein ApoC2 present on the surface of the chylomicron. So there will be an ApoC2 LPL binding that occurs. Now, ApoC2 that is present in the chylomicron, as well as other apoproteins such as ApoA5 that is also found in chylomicrons, these apoproteins will activate the lipoprotein lipase. It will activate this enzyme. This activated lipoprotein lipase will now break down the triacyl glycerol that is present in the chylomicron into free fatty acids and glycerol. These free fatty acids, most of these free fatty acids will be taken up into the tissue cells with the help of proteins such as fatty acyl transport protein as well as CD36. Some fatty acids might combine with albumin in the bloodstream, and they will travel as albumin fatty acid complexes in the bloodstream. So as more and more of this triacyl glycerol is broken down, this chylomicron particle is going to get smaller and smaller. These smaller chylomicrons are called chylomicron remnants. They are poorer in triglycerides, but they are richer in cholesterol. So as these chylomicrons become chylomicron remnants, they decrease in size. There is not enough space left. So some of these phospholipids, as well as the apoprotein C2, will get transferred from these remnants onto other lipoproteins such as HDL. Now, without the presence of A2, because it has been transferred to other lipoproteins, these chylomicron remnants cannot be broken down by LPL because A2 is required for the binding and activation of LPL. Now, in the liver, the ApoE and ApoB48, which is present on the chylomicron remnants, will bind LDL receptors as well as LDL receptor-related proteins, LRP, present on the surface of hepatocytes. So once these chylomicron remnants are bound to the surface of hepatocytes, there is endocytosis, and the chylomicron remnants are taken into the hepatocytes. So this is how we deliver triglycerides from the small intestine to the various cells in the body, and whatever the cells are not using, the rest of the triglycerides will enter the liver. This is also how we deliver cholesterol in our diet from the small intestine to the liver. This is also how we deliver fat-soluble vitamins from the small intestine to the liver. So this pathway is called the exogenous lipoprotein pathway. Now we also have an endogenous lipoprotein pathway. So let's talk about this endogenous lipoprotein pathway. So the liver makes a lipoprotein particle called VLDL. It uses the microsomal triglyceride transfer protein, or MTTP, that is present in the smooth endoplasmic reticulum, and basically it will add lipids such as triacylglycerol, cholesterol ester, phospholipids. It will add all of these lipids to the apoprotein called ApoB100. So the combination of all this gives us VLDL, and then the VLDL is secreted out of the hepatocytes. So the amount of VLDL that is made by the liver really depends on how much triglyceride it has. And also the more triglyceride that is present in the liver, the larger the size of the VLDL particles that the liver synthesizes. So when the VLDL comes out of the liver and travels in the bloodstream, it can absorb other apoproteins on its surface, such as ApoC2 from HDL or from the bloodstream. Just like in chylomicrons, when the VLDL enters the tissues, such as your muscle tissues and adipocytes, then the enzyme lipoprotein lipase will hydrolyze the triglycerides that are present in the VLDL into fatty acids, which are taken up by the tissue, as well as glycerol. So as tissues break down the triglycerides in the VLDL, we will form different subclasses of VLDL. So the large ones will be converted to the medium ones as well as the small ones. So eventually the VLDL will be converted into another lipoprotein called intermediate density lipoprotein, or IDL. So we can see here the VLDL eventually become IDL. Now this IDL that is rich in cholesterol esters, it will acquire ApoE from HDL in the bloodstream. Now the IDL will travel to the liver, and in the liver, the ApoE that is present on the IDL will bind receptors in the hepatocytes, such as LDL receptors, as well as LDL receptor related protein, or LRP. And this binding of the IDL with the hepatocytes will cause the enzyme hepatic lipase that is present in the sinusoidal endothelial cells of the liver to break down the triglycerides present in the IDL into free fatty acids and glycerol, which are taken up by the liver cells. And in the process, the IDL gets converted into various types of LDL, large LDL, medium LDL, as well as small LDL. So this LDL that is formed in the liver, here this LDL that is formed in the liver, this is predominantly cholesterol esters. That's the major lipid found in it. And the main protein would be ApoB100. Most of the other apoproteins that were on the IDL before it got converted to LDL, most of these apoproteins were transferred to other lipoproteins. So now we have the LDL that was formed in the liver from IDL. This low-density lipoprotein, LDL, now travels to various parts of the body, and the LDL will be taken up by the tissue cells of the body. The ApoB100 on the surface of the LDL will bind LDL receptors that are present in various tissue cells. The LDL will then enter the tissue cell by endocytosis. That will form an endosome. The LDL receptor may be recycled back to the plasma membrane. Now the endosome will combine with lysosomes, and lysosomes, as you know, have very strong hydrolytic enzymes, and these lysosomal enzymes will break down the LDL particle, and if there's any receptor that has not gone to the plasma membrane, that will also be broken down. The cholesterol ester that is present in the LDL will be converted into free cholesterol in the lysosomes by the enzyme lysosomal acid lipase. This free cholesterol will then be used by the tissue cells for various purposes. So this process by which LDL is taken up by a cell that involves receptors, this is called receptor-mediated endocytosis. So this is how cholesterol from your liver, the cholesterol from your liver present in LDL, is sent to various tissues. Now if there's any excess LDL present, that LDL will go to the liver, and the liver will once again, just like in case of tissue cells, take up the excess LDL by receptor-mediated endocytosis. Now the amount of LDL present in the blood is correlated with arteriosclerosis, and that's why we call the LDL cholesterol the bad cholesterol. So in arteriosclerosis, there is a lipid plaque that is formed, and the plaque eventually can rupture, form a thrombus, and that can lead to a heart attack or stroke, what we call cardiovascular disease. And that's a huge impact for human health. It's estimated that 17 million people die of cardiovascular disease per year worldwide. The exact mechanism by which LDL leads to arteriosclerosis is not clear, but we have some idea of the various processes that are associated in formation of the lipid plaque. It's believed that the oxidation of the lipids and or the proteins in the LDL, as well as a possible glycation of proteins in the LDL, that is, the attachment of carbohydrate to the proteins of the LDL, will cause the formation of oxidized LDL as well as glycated LDL. Now this oxidized LDL can aggregate, can join together to form very large particles. In fact, these large particles may actually look like microbes. These aggregated LDL that looks like simulated microbes, they'll be taken up by macrophages that are present in arterial walls. So they'll be taken up by phagocytosis, and now all these lipids will be present in the macrophages, and these lipid-laden macrophages are called foam cells. They're called foam cells. This uptake of the lipids by the macrophages lead to the activation of the macrophages, and that triggers inflammation. The macrophages will start releasing cytokines, a variety of cytokines, some of them will be responsible for the recruitment of other immune cells close to the macrophages. There will also be antibody formation, and all of these will result in the formation of a soft plaque of cells, platelets, as well as cholesterol crystals. This inflammatory process will cause the release of various proteolytic enzymes that will degrade the matrix in the arterial cell wall, and that can cause the plaque to be destabilized and the formation of a thrombus, which will then go and block some critical blood vessel and cause either stroke if the blockage is in the brain, or myocardial infarction or heart attack if the blockage is in the heart. So this is how cholesterol, LDL cholesterol from the liver, is sent to the various tissues of your body, including the macrophages present in the arterial cell wall. Now let's look at the reverse cholesterol transport. So let's see how, if cells have too much cholesterol, how does the cholesterol go from the cells to the liver? Because earlier we saw how cholesterol goes from the liver to the tissue cells. So hepatocytes, as well as intestinal cells, they will synthesize a protein called ApoA1. This protein is synthesized and then secreted out of the hepatocytes. Now on the surface of these hepatocytes, as well as the surface of intestinal cells and adipocytes, there is a protein called ABC binding cassette transporter 1, ABC1. And what this protein does, it takes cholesterol and phospholipids and adds it to ApoA1. And this will form what we call as nascent discoidal. So these particles look, they are flat, they look like disc, and we call this nascent discoidal pre-beta HDL particles. So these lipoproteins, these nascent HDL lipoproteins are formed, and this happens mostly in the liver as well as the intestinal cells. Now there are many processes in the body that will convert this HDL into other types of HDL. So there are a variety of HDL particles that we have in our bloodstream, such as HDL2, HDL3, 2A, 2B, and so on. So here are some of the ways by which we can form these various types of HDL that we find in our bloodstream. Now, in cells such as muscles, adipocytes, as well as many other cell types, including macrophages, they have proteins such as scavenger receptor B1 or SRB1, as well as the protein ABC binding cassette transporter A1, ABCA1, and ABC binding cassette transporter G1, ABCG1. These proteins basically will add cholesterol and phospholipids to the nascent HDL, forming other types of HDL. In addition, the cholesterol as well as phospholipids can be derived from the lipolysis of chylomicrons and VLDL by lipoprotein lipase. So these lipids can be added to the nascent HDL to form other types of HDL. The enzyme lecithin cholesterol acyltransferase, or LCAT, present in HDL, and this enzyme is activated by ApoA1. This enzyme can esterify free cholesterol, basically add a free fatty acid to cholesterol to form cholesterol esters. Now these cholesterol esters are more hydrophobic than free cholesterol. They will go deeper into the HDL particle, and in this way the flat nascent HDL particles will become spherical, larger, mature, spherical HDL particles. So that's another type of HDL particle which is much larger and rounder rather than flat. And then we have a protein called cholesterol ester transfer protein, or CETP. And this protein can transfer cholesterol ester from HDL into chylomicrons. It can transfer the cholesterol ester from HDL into VLDL as well as into LDL. At the same time, it can take triacylglyceride from VLDL or chylomicrons and transfer it to HDL. Now, when the HDL particles travel through the liver or through tissues, then we have the hepatic lipase in the liver or the lipoprotein lipase in tissues, and these enzymes can act on the triacylglycerols that is present in HDL and make the HDL into smaller HDL types. In addition, we have the protein phospholipid transfer protein, PLTP, that can transfer phospholipids between various HDL subclasses. So to summarize the role of HDL, HDL is made by the liver. It will go to various tissue cell types, including macrophages, muscles, adipocytes, and all of the other tissue cells in the body. And if those cells have excess cholesterol, they will transfer their excess cholesterol to the HDL. So the excess cholesterol is picked up by the HDL. And now we have this HDL with the excess cholesterol. And this HDL, through various processes, can become different types of HDL. So eventually, after 4 or 5 days of synthesis of the HDL which now has excess cholesterol taken from various parts of the body, this HDL will now be taken up by the liver. These steps involved in the uptake of this HDL by the liver is still uncertain. A lot of research is going on in this area. Basically, the HDL particle will bind to some sort of receptor, such as scavenger receptor B1, SRB1 on hepatocytes, or other types of receptors present on hepatocytes, as well as these receptors may be also found in the sinusoidal endothelial cells. And once this HDL is bound to these receptors on these cells, the HDL cholesterol is taken up by the hepatocytes, and this may happen with or without endocytosis, so we are not exactly sure. But eventually the cholesterol from the rest of the tissue will enter the liver. Okay, so that's how we get excess cholesterol from the rest of the body into the liver. And that's why we call HDL the good cholesterol, because it brings excess cholesterol from the rest of the body, including the macrophages, back to the liver for subsequent excretion. So this cholesterol, some of this cholesterol that is taken from the rest of the body enters the liver, and in the liver, some of this will be made into bile salts, which will then be stored as bile in the gallbladder. So the bile with its bile salts will travel from the liver and it will be stored in the gallbladder. In the gallbladder, a lot of water is removed, forming a very concentrated bile solution. And under the right conditions, we can have precipitation of this cholesterol or other components present in bile, and that can lead to the formation of gallbladder stones. So when you have a meal, the bile is released from the gallbladder. This is stimulated by cholecystokinin, and the bile salts will come out into the duodenum. And the bile salts will help emulsify dietary lipids that we talked about in previous videos. So this is the lipoprotein story. It is a long and complex story, and there's still a lot of steps that we do not know of, and there's a lot of active research in this area because of its close connections with arteriosclerosis and cardiovascular disease. Let us summarize the major things that we talked about. So after a meal, triglycerides are carried by chylomicrons. They go to various tissues where the triglycerides are broken down to fatty acids and glycerol for use by the tissues. And then the rest of the triglycerides are taken to the liver where they are broken down in the liver. Now, cholesterol after a meal from your diet, the cholesterol is also taken up by chylomicrons, and these chylomicrons will eventually become chylomicron remnants, and the cholesterol is sent to the liver. So this is how we send cholesterol in the diet to cholesterol in the liver. So chylomicrons are only seen after a meal. So a few hours after a meal, we should not see any chylomicrons because all the chylomicrons should be cleared by the liver. Now VLDL, on the other hand, is continuously made by the liver. So VLDL is how the liver feeds fatty acids. So the triglycerides in the VLDL are broken down and it feeds fatty acids. That is very important for energy to all the various cell types in the body. Those fatty acids in VLDL that are not required, they will be brought back to the liver in the form of IDL, and those fatty acids will be reused by the liver. Now, as far as cholesterol is concerned, LDL made by the liver will send cholesterol to all the tissues of the body, including macrophages present everywhere, including the arterial wall. Now, if cells had excess cholesterol, if the tissue cells, including macrophages, had excess cholesterol, then this excess cholesterol is brought back to the liver by HDL. So HDL is considered good cholesterol because it's bringing excess cholesterol back to the liver, while LDL is what we call the bad cholesterol because we are taking cholesterol from the liver and depositing it in various tissues. So we have the four major lipoproteins. So we have chylomicrons, we have VLDL, then we have LDL, and finally we have HDL. Before we end this video, a few words about lipid analysis in the clinical lab. This test for lipids involves what we call the lipid panel. And there's another test that we often do in the clinical lab, and that's called lipoprotein electrophoresis. This is lipoprotein electrophoresis. So in a lipid panel, a typical lipid panel, we measure total cholesterol, triglycerides, HDL cholesterol, and then LDL is often calculated using a formula. VLDL is also calculated using a formula, and a total cholesterol to HDL ratio is also often determined because that ratio is correlated with the chances of getting arteriosclerosis, which will eventually become cardiovascular disease. Another test that sometimes is done for lipoproteins is lipoprotein electrophoresis. So the sample is applied here on an agarose gel. Chylomicrons will, because they don't have much of a charge and they're very large particles, they will basically stay wherever you apply the sample. And then the next lipoprotein that will travel is LDL. This is your LDL. And then the other protein that travels a bit faster will be your VLDL. And then the protein that travels the fastest is your HDL, because HDL has a high charge and it's also a very small protein. Now, although this test is not done in the lab, but research-wise, we can separate the lipoproteins by ultracentrifugation. So the one that has the least density is the chylomicrons that will float on the top of the tube because it is very rich in triglycerides. And then next would be your VLDL, then next would be the LDL, and the HDL will be found at the bottom of the tube simply because it's very poor in triglycerides. It has the highest density. So the lowest density is chylomicrons and the highest density would be HDL, which will be found at the bottom of the tube. To give you an idea of size, the chylomicrons 80 to 1,200 nanometers. So this is the only one that crosses 1,000 nanometers. That becomes 1 micron. So that's why we call it chylomicron. So this is the only one that reaches the micron range. The rest of them are in the nanometer range. So VLDL is about 30 to 80 nanometers. 20 to 25 nanometers is your LDL, and your HDL is the smallest, around 5 to 12 nanometers. Just to give you an idea of a size, of a relative size, protein such as albumin is slightly less than this. So around the size, slightly smaller than an HDL. So that is all for this very long and complex but very, very important topic on lipoproteins. So thank you once again for watching. We'll see you hopefully in the next video. Until then, have a very happy and a very healthy day.